Hello all, my name is Ashutosh Rastogi. I am a teacher by profession. My mission is to impart quality education for all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Today we are going to discuss about introduction to the double sideband suppressed carrier systems. These are the contents. We are going to start up with the need of double sideband suppressed carrier systems, followed by the basic introduction to the double sideband suppressed carrier systems. Then we will try to formulate the mathematical equation for double sideband suppressed carrier signals, which will be followed by the frequency spectrum of DSBSC signals. Then we are going to calculate the bandwidth of double sideband suppressed carrier systems. Then we're going to calculate the power of the double sideband suppressed carrier systems, and finally we're going to conclude with the applications of double sideband suppressed carrier signals. So here is the need of double sideband suppressed carrier systems. This particular figure shows the spectrum analyzer view of our traditional AM signal. As we already know that our traditional AM signal consists of three basic components. One is the carrier signal, one we have upper sideband, and one is the lower sideband. Most of the power has been contained in the carrier signal, but actually carrier signal does not carry any sort of information signal. All the information or intelligence of the signal is being contained in our sideband, that is either in our upper sideband and in our lower sideband. Basically upper sideband and lower sideband, both the sidebands have got the same information signal. So for the sake of communication, if we do not pass the carrier signal, then we are not going to lose any sort of information till the time we are passing both the sidebands. As we have already mentioned that carrier signal does not contain any sort of information. All the information contained in our sidebands. So these are the sidebands which contains the information. If we need to design any communication system, then two of the most important parameter that we need to take care of is the transmission power and the transmission bandwidth. Since bandwidth is a very scarce resource and wireless devices are generally battery operated, so we need to focus over these two parameters. So obviously, if we are designing any wireless communication system, then we always require that it should consume as much less power as possible, and it should also be bandwidth efficient, or we could say that it should use very lesser amount of bandwidth in order to transmit the complete information. In the traditional AM, which is also being called as amplitude modulation double sideband full carrier system, both the power as well as the bandwidth requirement are very high, since in the traditional AM we are transmitting carrier signals too. So the transmission power can be reduced in the double sideband suppressed carrier systems by suppressing the carrier power. Obviously, we can suppress that carrier power since it does not contain any information. So in AM double sideband suppressed carrier systems, the transmission bandwidth is same as that of traditional AM system or amplitude modulated double sideband full carrier system. Since we are suppressing only the carrier signal and we are allowing both the passband, upper sideband as well as lower sideband, so obviously the bandwidth requirement is same or analogous to our traditional AM system, but we are in a state to substantially reduce the amount of power in comparison to traditional AM signal. So obviously to accomplish these merits, the equipment design is more complex. As we know that for generating traditional AM signal, any sort of non-linear device could serve the purpose, but since we need to suppress carrier signals and we have to perform certain more complex operations in order to generate double sideband suppressed carrier signals, then obviously the equipment design will be more complex. So now we'll try to find out the mathematical equations of double sideband suppressed carrier signals. So the generalized expression for AM signal is being given as modulated signal ST will be equal to AC cos of 2 pi FCT plus AC MA cos of 2 pi FMT multiplied with cos of 2 pi
FCT. So here this expression AC cos of 2 pi CT is your carrier signal, and AC MA cos of 2 pi FMT multiplied with cos of 2 pi FCT. This expression shows our sidebands. So obviously if we have to save the power, then we need to suppress this carrier signal. If we are in a state to suppress that carrier signal, then the remaining available signal are the signal which only contains the two sidebands, that is your upper sideband as well as the lower sideband. So in order to generate double sideband suppressed carrier systems, we have to subtract or reduce or suppress that particular carrier signal. Expression for double sideband suppressed carrier signals would have been given as AC MA cos of 2 pi FMT multiplied with cos of 2 pi FCT. Here we have multiplied by 2 and we have divided by 2. We have expanded this formula to cos A cos B as cos of A plus B plus cos of A minus B. So we have cos of 2 pi FC plus FMT and cos of 2 pi FC minus FMT. So the higher frequency components, that is your FC plus FM, will be called as our upper sideband, and the lower frequency components FC minus FM will be called as your lower sideband. So this particular figure shows the spectrum of double sideband suppressed carrier signals. This particular signal actually shows the spectrum of our message signal. Obviously, we are assuming a band limited signal in which maximum frequency component is FM and its frequency domain will have been represented by this particular figure. So after modulation, when we have applied the carrier signal, obviously the spectrum will get translated or shifted around the carrier frequency Fc. So we have this particular figure which shows the spectrum of double sideband suppressed carrier systems. We have this upper sideband which lies in the range of Fc and Fc plus Fm, and we have this lower sideband which lies in the range of Fc to Fc minus Fm. So this is our upper sideband and this is our lower sideband, and these two particular bands are the negative frequency part or negative frequency counterparts of our upper sideband and lower sideband. So obviously with this figure we could say that the maximum frequency component that is present in our modulating signal is Fc plus Fm, and the lowest frequency component that is present in our DSP-SC signal is Fc minus Fm. So I mean in our DSP-SC signal we will not going to get any frequency component greater than Fc plus Fm, and we will not going to have any frequency component which is lesser than Fc minus Fm. This particular figure shows the spectrum of single tone DSP-SC signal. As we know that single tone signal is the signal which only contains a single frequency. So this particular above figure shows the spectrum of our single tone signal which only have the single frequency plus FM hertz, and this particular minus FM shows the negative counterpart of our signal. So after modulation, we have this particular sort of spectrum. Maximum frequency lies at Fc plus Fm and lowest frequency lies at Fc minus Fm. And these two components are showing the negative frequency counterparts of our upper sideband and lower sideband signals. This is our upper sideband and this is our lower sideband, and these two are the negative frequency counterparts of our upper sideband and lower sideband. So bandwidth of double sideband suppressed carrier signals. We know that the bandwidth of any signal would have been given as the maximum frequency component subtracted with the minimum frequency component. Basically, bandwidth means the range in which a particular signal will be going to lie. So here Fmax is the maximum frequency component of the signal and Fmin is the minimum frequency component of the signal. Obviously, by bandwidth, we mean that the signal will going to contain in that range of frequencies, means the particular signal will not going to have any signal beyond its maximum frequency, and it will not going to contain any signal which is less than its minimum value of frequency. So from spectrum figure, it has been clear that maximum frequency in our double sideband suppressed carrier signal will be at Fc plus Fm and minimum frequency is Fc minus Fm. So after subtracting minimum frequency from its maximum frequency, we are going to have this expression twice of Fm. It means the bandwidth of our double sideband suppressed carrier signal is same as our traditional AM signal, equal to twice of FM, where FM is the maximum frequency component of our baseband signal or message signal. So now we'll try to find out the expression for power of double sideband suppressed carrier signals. The generalized expression for DSP-AC signal is being given as AC MA by 2 times of cos of 2 pi Fc plus Fmt plus cos of 2 pi Fc minus Fmt. So the power of the double sideband suppressed carrier wave is equal to the sum of the powers of both the sidebands, that is our upper sideband as well as our lower sideband. So the total power is being given as the summation of upper sideband and the lower sideband. We know that the electrical power can be calculated as the root mean square value of the voltage divided by the resistor R, where root mean square value would have been calculated as Vm by root 2, where Vm is the maximum value of our voltage signal. Here one thing I need to mention, that we are assuming that our message signal is varying sinusoidically or cosinusoidically. In that terms, we'll be having this expression for root mean square value of our signal, that is equal to Vm over root 2. If the signal variation will be of different kind, then obviously the RMS value of that particular signal will going to change. Since we are assuming cosinusoidal variation of our signal, so root mean square value would have been calculated as Vm over root 2, where Vm is the maximum frequency component of our message signal. So referring to our previous derivation that we have done in our previous classes when we were studying traditional AM systems, we know that the sideband power can be calculated as AC MA by 2 root 2 complete square by R. Here we just have put it down the value of Vm as AC times of MA by 2 from the previous expression. So power of upper sideband will be equal to power of lower sideband, which will be equal to AC square MA square by 8R. So in order to calculate the complete power of double sideband system, we need to add these both upper sideband as well as the lower sideband. So here we have total power will be equal to power in the upper sideband added with power in the lower sideband. So total power would have been calculated as AC square MA square upon 8R plus AC square MA square upon 8R. It represents the power in the upper sideband, and this particular expression represents the power in the lower sideband. So after adding, we'll be having AC square MA square upon 4R, which is nothing but the total power of the double sideband suppressed carrier signal. These are the certain applications of double sideband suppressed carrier signals. DSB transmission is mainly being used in the applications where the power saving is more important. Obviously, this is the reason why we are using this suppressed carrier systems. It has also been used for TV broadcasting. Nowadays, we'll be having digital broadcast systems, but when we are doing certain analog broadcast, it has also been used for TV broadcasting or video transmission. It has also been used for air traffic control radios, information exchange, some keyless remotes. It has also been used for two-way radio communications such as walkie-talkie, etc. These are the references. Thank you very much for your patient hearing.